So right now we want to find the area of a parallelogram. A parallelogram is this figure right here that I have on the board. And to review what area is, the definition of area is the number of unit squares that fit in a 2D figure. So we look at our parallelogram, has a bunch of squares, and we might think, okay, let's just count the squares. 1, 2, 3, yada, yada, yada. But we run into a problem, because if you see right here, the squares got cut. It's not clear how many squares there are right here. Also right here, we're going to take like a fraction of a square or like a decimal of a square. That's too much work. And at the end of the day, it wouldn't even be accurate. So what we're going to do to derive the equation of a parallelogram is first we're going to look at what a parallelogram even is. A parallelogram is a four-sided shape. This shape has four sides. Is a four-sided shape whose opposite sides are parallel and congruent. And in class, you should know that congruent means the same length. The sides have the same length, and they are parallel. And that's actually very important when we're going to derive the area of a parallelogram. So since the sides are parallel, this right here, this side right here, is the same length as this side right here. So we can do a transformation of this shape and make it to look like another shape that we're more familiar with. So let's say I have a pair of scissors and I'm cutting up here. So I'm going to make a straight vertical line cut like this, and I'm going to remove this part of the parallelogram. So I'm taking this out. I cut this up, I remove this triangle, and I'm going to translate it to the left, and I'm going to fit it right here. Since they're parallel and congruent, I know that it's going to fit perfectly, or if I am able to put it perfectly. All right, good enough. All right, so I moved my parallelogram. So I cut it up, this triangle, and moved it here, and it fits perfectly into this shape. And this shape is a shape we're all familiar with. It is a rectangle. And we should all know the area of a rectangle. It is length times width. You're multiplying the two sides together. And because we did this transformation, look how all the squares are now like perfectly even. How we can see all the squares. So if we want, we can count it, but we're going to use the equation of a rectangle. Area, A, equals length times width. So for this parallelogram, I'm going to calculate the width. How many squares is in the bottom? 1, 2, 3, 4, 5, 6, 7, 8. The width is 8. And I'm going to calculate the height, or the length. 1, 2, 3. Actually, let me use my red marker. 1, 2, 3, 4, 5, 6. The length is 6. So we're doing length times width, 6 times 8, and that equals 48 square units. And you may be thinking, okay, but isn't this the equation of a rectangle? Why can't we do it in the parallelogram? The reason why we could do it in the parallelogram is because by using our transformation, by cutting up the triangle and moving it here, we made it into a rectangle. And that's actually a very special property that a parallelogram has. Any parallelogram you can cut up and make it into a rectangle. And because of that special property, the area of a parallelogram is the same thing as the area of a rectangle. I'm going to, again, I did not leave myself space, but area of a parallelogram is the length times the width, or base times height. It's the same thing. Length times width, or base times height. And I'm just for a reference, I'm going to transform my rectangle back into a parallelogram. So I'm going to take this triangle, I'm going to remove it. I'm going to move it back here. It's the same thing. We're doing the width times the length, the vertical length up here. And that is the area of a parallelogram, the same exact thing as the area of a rectangle.